Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about India's indigenous fast breeder reactor. So let's dive deep into it. So what we are talking about? Well, it's India's first indigenous, meaning we built it, every component of it, fast breeder reactor. I'll explain these part later. Now, you must understand this. Whenever you're talking about nuclear power plant, there is a tendency to demonstrate energy in two units, meaning you will have 500 megawatt E. Like what is that E? E simply means electrical, because they generate a lot of thermal power. So there is a general different meter for thermal power also. So you may get like 1500 megawatt, but does not mean it's 1500 megawatt electrical. So that's why E is there. Whenever you are dealing with nuclear is one of those things. Pay attention in Chernobyl TV series, you will find the same thing. So 500 megawatt electrical power at Kalkampur, Tamil Nadu. So it's basically at the tip of India. The big city is Chennai. It's not like you can land in Chennai and just walk there. It's a bit far, but it's there. And it's fully designed and constructed indigenously, meaning even small companies got a lot of business because of this. Every part of it. It was very inherent to the design of it. And what it's going to use right now as a fuel is uranium plutonium mixed oxide as the first generation fuel. And over time it's going to have a blanket of uranium 238. That's going to be the blanket part, and then it's going to be in the breeding one. Basically it's going to go from a non-useful uranium to useful uranium. So this is the building, and Prime Minister just inaugurated, meaning they pushed it beyond criticality, meaning this puppy is now live. So this is what we are talking about. So what's the aim of this? Well, aim is India had a very long term, like a surprisingly long term, three-step plan. Now, the aim of that plan that was laid out in 1954 is that once we're at the last stage of it, we should reach self-sufficiency. So you have to understand this. Core technology, even in 1954, there were a lot of nuclear technology, but it was under hush-hush secrets and all that. Heck, it was so secret that members of NATO alliance itself was not trading secrets with each other. So there was a serious climate where there was like, if you want this technology, it's better to actually build it yourself. And what we actually wanted to achieve was not done to this point. Even in year 2024, the technology that we want does not exist as a like take it and go. Prototypes exist, but not as like a final product. So we realized very early on, as in 1954, that we have to build the core technology from start to finish, so we can deploy indigenously in India. So from day one, we wanted that sort of independence. Now, why do we want to go through this route? Well, the reality is, based on your geography, you get certain things or you lose certain things. For example, most of nations on this planet does not get neodymium. China gets it. It's one of those things. Like most nations do not get oil. Arab nations gets it. It's one of those things. You do not select it. It's just like it's there. India's case, India gets boatload of thorium, almost negligible amount of uranium. So it's like, it's not like we do not have uranium. It's like it's just flat out not worth for us to mine it. Again, if it's absolutely necessary, weapons grade, criticality, we're gonna get it done. But it's not economical, so to say. However, in terms of thorium, we were selling thorium to USA in 1950s. That's how much thorium we have. Like it was like, bro, we got this. That's how much we have. So we needed a technology that can utilize this abundant resource that India has in terms of thorium. Now, what will be the benefit of it? Let's say India goes through this long process. What will we get at the other end of it? No more import from either Russia or France or other nations also. We have like a lot of suppliers. So these are the two major suppliers, France and Russia. So we want to have independence where we are no longer dependent for our energy from any independent supplier. So what's the step one? There are three stages to this. Step one is take uranium, buy uranium. At this point, we are buying it either from Russia and France, get energy out of it, but you will get plutonium as a waste. So we get plutonium out of it. Now, plutonium, we do not waste it. We utilize pressurized heavy water reactors, nothing fancy, known technology, stable technology, and very good at creating, basically converting uranium into plutonium. We take plutonium out of it. Now, take plutonium, mix it with thorium, that gives you uranium-233, that is useful uranium. And to achieve this, basically the forceful marriage of plutonium and thorium into something useful, basically not marriage as it like transmutation, you need fast breeder reactor that we are talking about now. And then once you have this fast breeder reactor, now you can create a starting charge. It's almost like how you have a starter motor in your car which just runs on battery but does not run your car. Same thing, if we do not have this breeder reactor, going to the final stage where we are directly using thorium, it's very difficult to do. So fast breeder reactor is the next stage for us. And then once we have done that, we will take thorium 232 and then convert it into uranium 233. And to do this stage where you are taking raw basically thorium and converting it to useful nuclear fuel, you have to utilize advanced heavy water reactor. So how the heck that will happen? Basically, you're going to have transmutation. You're going to have neutrons, thermal neutrons in this case, thorium bombardment, and then thorium is going to become unstable. It's going to go through beta decay, then it's going to go one step below, and then it's going to go one step below again with beta decay, and then it's going to uranium U92, as in U33, useful fuel, and that can be running in the reactor itself. However, you may pay attention to the fact that we are talking about 2 water reactor, 1 fast reactor. So because of the chemistry and like nuclear dynamics, how this is happening, we need different things at different stages. We could not directly just start with, okay, we have thorium, let's build a nuclear reactor. It does not work that way. Not in the scales that we are talking about. It's one thing to do it in lab, another to like actually do as a power plant. So this was the aim. The idea is that at the end of it, once we reach this final stage, we're gonna have independence for our nuclear industry, meaning we do not give a damn whether Russia and France starts fighting and they're like, we're gonna sanction you, and it's like, we're like, who cares? We got this. We got this. We're sorted. So that's what we want to reach at the other end, where we have thorium transmutation as a like, don't even give a damn. Like, put thorium, we got energy, done, go home. So this is the aim, long-term processing. And this also reduces the waste that India has to deal with, because the waste plutonium is now useful for the second stage, and outputs from the second stage is now useful to the last stage. So it's literally also waste reduction. So at the final stage, we're going to have exponentially less waste, comparatively speaking. So how this puppy is built? Well, this is the best design that I could find. Now, 500 megawatt electric system. You have to understand, this is a pool type system. We are using liquid sodium as primary heat exchanger fluid. Like, why? Well, here's the deal. Water is good and all. It has very high thermal capacity, but it does suffer in terms of temperature. It does not get very hot before it boils. So you are only talking about 100 degrees Celsius. Not a lot of temperature, but you need more temperature in order to boil enough steam to do anything useful. So for that reason, all the normal reactors generally have very high pressure water, and they are generally operate at more than 300 degrees Celsius. But you must understand that requires not only a very robust against corrosion, because again, hot water is very different kind of destructive, and you're talking about very high pressure. So cost of plumbing becomes exponentially high, and in terms of temperature, you do not have much leeway. However, when you are dealing with liquid sodium, all the pressure drops, meaning your pressure could be ambient pressure, 15 psi, 1 bar. You do not have to worry about it. And it runs much hotter for that pressure. So actually, you can even exceed what general normal reactors can do, because there is an upper limit. Even if you're like, what if we have 10,000 bars of pressure? Yeah, if you have too much heat going into water, water will thermalize, meaning it will break into hydrogen and oxygen on its own. So there is an upper limit how hot you can get it. However, when you're talking about sodium, that temperature can go up to around 800 degrees Celsius before it starts to boil. So you have lot of room, like a lot of comfortable room. So the reactor is hot. It's around 547 degrees Celsius pool. Hot puppy, basically it's very hot. And then we are carrying around 525 degrees Celsius to the heat exchangers. That is running the high pressure steam turbines. Then you have recirculation, reheat and all that jazz. And then basically condensing the waste steam, we are using C. So it should work in all seasons without ever running out of water issue, because again, ocean is not running away. Actually, it's coming to us, so we do not have to worry about it. That's the condenser part, and that's how your water loop is working. So 525 degrees Celsius is the input temperature. Output is 255, basically after dumping the heat. And you may like, that temperature is hot enough in many other nuclear plants. So we are getting much higher thermal efficiency. You always want the T delta between the condenser water and the feed water. So there is a lot of delta. So you get a lot of efficiency. That's the good part. And C is used for cooling. So we'll not be worrying about that issue that France had, where it's like, oops, in 2022, a lot of nuclear plants had to tone down their power because they were boiling reverse away. And again, once you boil enough water away, the surface area shrinks, it becomes a cascading effect. So We will not suffer that issue. Now here's the deal. One core component you have to understand: nuclear reactor do not have off switch. You cannot just like off. It does not work. So what happens when you turn off? All you do is insert controller. What does that do? That stops fission. That's absolutely true. It does nothing to the decay products. So decay products still generates it, and you are talking about nuclear decay. So you could be looking into something that requires cooling, lot of cooling for long duration. How long? Well, if you know anything about nuclear fuel, you know spent fuel sometimes require 2 years in a liquid cooled fuel. 2 years spent fuel. So let that be very clear. For there is no reality where you have a nuclear reactor and just like off, me good. That's not how it works. What you have to do is like once you turn it off, keep cooling it. And this is how Fukushima went to boom. It's like they had earthquake. Okay, everything is fine. They had flooding and everything is fine. Control rod goes in, reactors off, everything is fine, everything is dandy. Then why did it went boom after it? Well, this is the part. You have to understand, Japanese ego is a thing. So Nuclear Safety Commission did give them a warning that all of your backup generators are in basement level, meaning if any flooding event happens, you're done, you're dead. Why will you be dead if you have backup generators that are flooded? Well, here's the deal. Once you turn off the reactor, you no longer have power. If you no longer have power, how the heck you gonna run the pumps that are needed to pressurize the water in order to cool it? Because if you do not put pressure water, if you're like, okay, I have a tank, I'm gonna feed it, yeah, water will not go there. The steam will create a blockade. You need pressurized water. So that for that much pressure, you need pumps. For that pump, you need energy. Energy comes from generator. And they did not have like proper safety procedure where like some generators are top level, some are medium level, some are basement level. They had all in basement level because Japanese ego. It was in a written letter. So again, flooding happened. And the same thing here could happen, where it's like, okay, you inserted control on, now what? Well, thankfully, they thought of it. So this puppy has 4 passive decay heat system removals. And it's taking the heat from sodium, dumping into air. Now, the benefits that we have here is the temperature delta. So temperature delta from India is hot environment. So how hot can be for us? Well, let's say worst case scenario, 61 degrees Celsius air temperature. Here's you. What is the temperature of sodium here, liquid sodium? That is 500 degrees Celsius. What does that mean? That simply means if you have a good design, you can have sodium convectively moving. So we can literally have a structured diagram that moves the sodium into a air to sodium heat exchanger, and that air takes all the heat away, because again, from air's point of view, even its hot Indian air is like 60 degrees Celsius. It's like, bro, 500 degrees Celsius. It's taking all the heat away without fans, and then it just cools down, falls back in. There is a bladder values, and there are some auxiliary units to make sure this process is very efficient, but no electrical required. The only part that is even electrically activated, that is the louvers that is controlling the airflow, and louvers are designed in such a way that it cannot be off. It's minimum or maximum. So even at minimum, it will work, and there is no electrical requirement for it. And there are 4 of these puppies. Each of them can dump 8 megawatts of thermal heat. Each of them has 4 of them. So, and this also allows the maintenance and downtimes to be far more easily manageable. So again, that's why passive system was focused on, because again, we may need to pull in and pull out a lot of stuff regularly. So having a passive way to making it safe is desirable. So it has passive system. Now, what does this fast mean? Well, fast in simple terms means no moderator, meaning your neutron that is being emitted is going YOLO. So you're not putting carbon in there to slow it down. You're not putting water there. Now, like, how can water slow down neutron? Water is only the thing that can slow down neutron effectively. Like if you have the given amount of length, water is one of the best shield. Why? Hydrogen. Why? Hydrogen takes neutron and steps up. So it can go from deuterium to tritium. So it has 2 stages to go up and climbs up very easily. So it's a very good way of taking high speed neutron or fast neutron and converting into thermal neutrons. But for this design, you do not want that. For breeder design, you generally do not want fast neutron. You do not want thermal neutron. You want fast neutron. So you have to design something that does not use water, because water is a moderator. Here, sodium is transparent from neutron's point of view. So fundamentally, you are achieving fast neutron. And reactor is also negative void coefficient. What does that mean? That simply means assume something bad happened. Poof, this part, this whole liquid section, this is energy leaching section, goes poof. And you're reaching a point where control rod is not deployed. What happens? This part boils. Okay, boiling, what does this mean? Simply means it will go from, let's say, 540 degree Celsius of operating temperature. It will start to climb 500, 600, 650 degrees Celsius, but it will also slow down the reactor on its own because the behavior is negative coefficient. So it will tone down. So there is an auto throttle. It will not run away. The negative coefficient is always desirable. If you watch Chernobyl, that's what they were positive. Here is negative, meaning if something goes wrong, it automatically, most of the time, it will go in a positive state where it's like, okay, I'm chilling down on my own. So it will not boil to a point where literally sodium will boil away. That should not happen. So it has that. And what is the breeding part is basically taking fertile material, making it into fuel material. So it's the best way I can describe this breeder reactor, because way too many people say it makes more fuel. It's think in this way. You have a forest and you want to run a charcoal furnace. So you have to have an extra stage in between. So what this furnace does, this breeder reactor does, it burns the charcoal, the plutonium that we got from the last stage, and then using the waste energy of it, it converts wood into charcoal. So you are running your plant from charcoal. Charcoal's waste heat is creating a next generation of charcoal. So your wood is being converted from useless wood to useful charcoal, and you are burning the charcoal. So same thing happening here. So input is there. We are putting fissile material there. It's just not fissile, as in like a nuclear material. We are putting nuclear material, it's becoming useful nuclear material, and then it's being consumed. So it does consume nuclear material directly, but it generally makes more as in more useful one. So if you put 5 ton, it will not come out more than that. It will be 5 ton only. But after conversion and all that, you can have like 5 kilograms of useful material and 50 grams of useless, 50 kilograms of useless one. The useless one will become useful. That's the whole point of breeding. So this is the design of it. So it's a pool structure, and actually the pump is inside there, like the turbine part. The pump is inside. So it's a bottle, inside another bottle, and properly contained from all sides. And very hot, very high efficiency with passive backup systems, 4 of them. So this is the whole design of it. So why now? Why this attention now? Well, the reality is, world's first sodium-cooled fast reactor was built long ago, as in USA 1951. It's ancient technology. And I do find it odd that I've seen way too many nuclear people talk about sodium. Sodium. It's like, dude, we know. We used it. We built it. And many other since also was built. It's not like, okay, USA built it. Like Russia built it. If I'm not mistaken, Canada also experimented with it. Germany, France, all that jazz. A lot of country worked onto it. The reason why it was never preferred over water is that if water requires, let's say, 50 stuff to deal with its pressure and temperature, sodium required way too much more. So the hassle was never worth it. Why the hassle? Well, it burns in air and explodes in water. Yeah, that's an issue. So when NASA is building a nuclear power system that is running on sodium with design for vacuum, it's kind of easy. You do not have to isolate it from, let's say, atmosphere or water. But in vacuum, you do not have to worry about it. Here, you have to worry about it. So those things became an issue. To give you a context, like to put in real world context, this puppy, that is Russia's BN600 series nuclear reactor that is running on sodium, yeah, that puppy had 27 leaks in 17 years. It had more than 1 leak per year. A nuclear reactor. Any of them could have gone out of hand. So be mindful. More than enough people have tried it, learned the hard way that it's flat out not worth it. So that's why we are sticking to water systems. Because again, something that explodes when you have basically have water touching it and burns if air touches it. So yeah, that's inside a human environment. It's a kind of difficult to do. So, and what about thorium? Thorium reactor have been tried from very long ago, as in like 1962, but it was never mature. Why it was not mature? Because thorium, people have looked into it. Again, USA bought a lot of thorium from India. So a lot of research was poured into it, but early on people figured out uranium equal boom, equals very big boom, equals mine is bigger than your booms. But thorium was not so attractive in that regard. So people focused on mine is bigger than yours. So more attention was focused on uranium. Then somebody else looked into it. It's like, okay, I can make even bigger than your booms. So everybody focused their ass off on uranium. Uranium technology developed exponentially. The whole supply chain was made. To give you a simple context, on paper, thorium should be cheap. In real life, thorium is so expensive that whole uranium ecosystem, even when you have to buy from France or Russia uranium, is still cheaper than thorium. So that's why nobody uses thorium. It's like, it's not a new technology. We know how to do this. It's just that it's not mature enough where it's like, you know, the cost. You have to do it from day one. And that's another aspect, is like why India was focusing on developing the technology. It does not exist to same extent where it's like uranium reactors, you can just pick up a phone, ask a General Electric, and they're going to give you a like delivery and quotes and all that. But thorium reactor is like, they can do it. It's like, yeah, they're going to charge arm and a leg. So India took decades to develop to the starting point of this technology. Let that kick in. Like to build the whole pipeline. And India is like trying to build the whole system, where how you're refueling the system, how you're maintaining the system, how you're managing the plutonium waste, how you're refining the other filter, everything. All of that took decades to do. And again, it still will take more decades before we reach a point where it's a mass production. We are just at like stage 2, like level 1 of stage 2, lot of way to go. So it's a very, very long process. Then why we are doing it? Well, even Russia, when they built it, they do have some of these reactors. Just like majority of the reactors are not this design for this exact reason. It's hell of a hassle. And at the end of the day, a power plant reactor only has one thing to say: electricity. If it has way too much hassle, it becomes costly to run. So your watt hour price goes down. Price goes up, sorry, and attractiveness goes down. So India is in a unique place where we have hungry nation and a growing nation. So our power consumption is going up and our industries are growing. So we are needing exponentially more power. And we have planted this seeds long ago. And be mindful, you are talking about 1950. Ain't nobody got time for a solar or wind at that time. So world was very different when foundation of this technology was laid down. And again, people lost interest in nuclear is simply because it's too expensive. Everybody tried it, came the same thing. It's too goddamn expensive. And you are talking compare this technology with solar and wind. Solar and wind are the both technology sections where the prices is going down. And we crossed the threshold in early 2000 where we were like, oh, it's a good joke. It's like it cannot provide power. We crossed that threshold. Now it's like figure out a way to store the energy. We got the energy part sorted. So that's why nuclear is not that attractive as you think. Especially if you have to pay for it. If you are talking about an aircraft carrier, who gives a damn? But if you're talking about like an actual energy system, yeah. That's why people do not like hassle. That's why people want to make sure that, because again, you only have energy to sell. If you're like, hey, I'm using this super new fuel, which is exponentially more expensive. Yeah, no. So that's why. So does India need this approach? Well, reality is politics of nuclear physics is very, very complex. It's like, and there is a good reason for that. And India had like really bad experience with people, which includes China, includes USA, includes Canada, a lot of bad experience there. So, and India is the reason why every other nation, especially Western nation, they are not comfortable giving anybody else civilian nuclear technology. We kind of gave a bad reputation because again, energy is energy. If you have enough technology to run a nuclear plant, converting into boom boom powder, it's not that difficult. We proved that. Like we got the technology from Canada and all that. But to be fair, Canada's design was way too silly and way too open. It was like, okay, you have fuel rod. It's making plutonium, but here's the deal. If you let it be there, plutonium gets overcooked, goes into a different state where it's not that boom boom capable. But the design was such a way that you can pull it out while the reactor is running. You do not have to shut down the reactor. So you can cook as much plutonium as you want. So India had that. And other American designs also. But like it was very clear early on that if you have brain power to make nuclear energy, you have brain power to make boom energy. It was like that Pandora's box was open. Once Oppenheimer opened that box, it's done. So India created that sort of reputation where it's like, yeah, you cannot give any other nation a nuclear technology because they will figure out how to make boom if they want to. Let that be very clear. If they want to. We could have done this very early on. We did not, simply because we were not scared. Once we got scared, because India, Pakistan and Bangladesh, they had a boom boom happening there. That time China was like, we're gonna join into the war. To stop China, USA dropped their aircraft carrier, which had a nuclear armed missile. And India took it as like a sign, what are you doing? And like the reality was they wanted to stop China. So because if China comes in, Russia will be joined in and then it could escalate. So they wanted to make sure that China does not drop in. So they took put some pressure. Yeah, that escalated badly. After that, India was like, yeah, we need our own boom devices. You guys are not trustworthy. And I do understand it. Like, I do not blame my ancestors who did this. It's like, yeah, I understand. It's like, you have boom, I don't have boom. That's not acceptable boom. So I get a big boom boom. So I do understand it. Like from a nuclear point of view, you need that power. Again, after first detonation and actual weaponization, we waited for 20 years. Like, we did not have a need for it. We did it inside. So, but in terms of India's national power, we do need nuclear navy. Now, we have already started in this. We have a nuclear powered submarine, and which is nuclear armed also. So this is a good puppy. And we are going to scale up slowly over to nuclear powered aircraft carrier. Now, nuclear powered aircraft carrier is kind of necessary. Why? This is one thing that you do not understand when you're comparing it to diesel powered system, is that diesel powered system has small engines, huge tanks. Otherwise, they will not last for months. So you have huge tanks. Here's the issue: the space is limited. The aviation fuel on board is much lower. So if you have a diesel craft and a nuclear power system, same size, if they go into battle, this puppy will have exponentially more flight time, nuclear powered one. That's why super carriers are designed in such a way. And when they are scaling it, it's like, might as well make it bigger. So then they get exponential more better. So India needs a navy. And again, why do we need it? One side we have China, another side we have freaking Pakistan. So yeah, we need it. So fundamentally, we need bigger puppies of this. So we do need nuclear technology. And if it's a fully developed, indigenously built, not only are we going to get economic benefits of it, and the development of technology has its own benefit, we're going to get a lot of spin-offs benefits of that. However, that's for the nuclear power. If India wants nuclear, go nuclear. Technology development, awesome. In-home technology development, ultra awesome. As a energy source, as in like energy for plants and industry, yeah, it's dubious at best. It's one of the things, every Tom, Dick, oh, nuclear is like, I've only seen one people who was like actually genuine, Rolls-Royce engineer, they're working on small nuclear. Yeah, it's not going to be cheap. It's going to be so expensive. It's like, it's worthless. Only for military, it will make sense. Why? Yes, you need security. Security is expensive. And you are talking about nuclear system. You need exponentially large size security apparatus just to store that. And economics does not make sense for making small one. Somehow people are like, oh, we're going to have sodium. It's like, yeah, we had it. We're going to have this. We had it. We're going to have this. It's just not cost effective. And oops, it does not tolerate. So this is Fukushima. This is Chernobyl. So all the reality. And even France is dealing with this. They're like, oh, France has so much power. As if like year 2022 did not happen. Where they're like, actually we have to shut down the power because we're going to boil off the rivers. So yeah, so it's one of those things. On paper, it always makes sense, but in real life, it's like the cost. Again, you are only selling something, and be mindful, there is a competition now. It was not there in 1950s. 1950s, there was no cheap solar. 1950, there was no offshore wind. Now there is. Now we are reaching a point where nations are realizing, hey, it's much cheaper to put a giant solar farm in different time zones and connect them with utilizing undersea high voltage DC cable, and voila, now you have power for 12 hours a day. Problem solved. Shut up. Take money. Get it done. No problem. No cost overrun. No basically, oh, it's supposed to be built in 5 years. It took 15 years to build. None of that. And none of the oops event possibility was also there. So, oh, ROI is actually there. In nuclear, all of them are negative. So, fundamentally, nuclear is neither cheap nor abundant. On paper, yeah, we can scale it up. Scale it up. Now the cost becomes stupid. And be mindful, 500 megawatt is expensive. 2 gigawatt is very expensive. And 2 gigawatt solar farms are being built almost annually in India right now. In India. So fundamentally, should India develop this technology? Absolutely. We need nuclear powered navy. We really need it. So awesome for that. As an energy source, yeah, no. The world has changed too much. So from economics point, and again, it's like everybody is like, oh, we have safe design. Everybody thinks it's safe until it goes boom. And when it goes boom, all the savings that you had throws away in 1 month. So that's why. And again, why we are not worried about this? They are sleeping next to boom boom devices. If I can trust them with that boom boom devices which can remove the planet from orbit, I'm okay with it. So there is a need for it. But as an energy source, dubious. Next video, I'm going to talk about like why nuclear always looks so awesome but never works out in real life. So this was my presentation on India's nuclear fast breeder reactor. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.